All right, great. Welcome back, everybody. I'm going to turn it over to Miriam again, who is going to be talking about full system simulation.
Okay. Hello again. So I'm going to talk about gem5 full system simulation. And we're going to talk about mostly about why we do full system simulation, why we do the steps that is required to do full system simulation for gem5. And at the end, we're going to see a useful tool for gem5 full system analysis and an example. Before starting, let's do another out of order action item. I'm gonna ask you all to go to gem5 directory again and build gem5 binary for RISC-V and make sure that it's optimized. So we may use a couple of debug flags as well. So I'm going to switch to code space as well. Where is it? Okay, let it run in the background because it can take up to like 15 minutes to finish. We don't need it now. We're just going to use this for the example at the end of the presentation. Okay. So we're going to go through a little bit of introduction to gem5 full system mode. We're going to become familiar with the basics of booting up a real system versus what happens in gem5. We're going to see how we can create a disk image by Packer and QEMU, how we can use the kernel binary that we can create for ourselves based on the requirements that we need, and extend or modify the available gem5 resources. And at the end, we're going to see M5 term, which is a tool to do some debugging and stuff like that for full system. A little bit of introduction about full system simulation. So what is full system simulation? So it means that a type of simulation that considers the entire computer system, starting from processors, memories, peripherals, IOs, networks, and the complete software stack, including operating system, the applications, or any device drivers. So what happens for gem5 when it's working on full system mode? So just as expected, gem5 also tries to simulate the entire hardware system from CPU to IO devices, memory, everything. And the good thing about gem5 full system simulation is that it allows us to execute binaries without any modification. And also it enables us to do research on operating system stuff if we need to do anything with the operating system, like making a library, things like that. Definitely we need to go with the full system mode, not SE mode. Let's see what gem5 needs to launch a full system simulation. We need the gem5 binary, which can be any type of binary according to your ISA, as we have seen many, many times in the past couple of days, like x86, gem5 opt, or ARM. We need the config file, which describes the system, for example, x86 NAS parallel benchmark, which is usually in Python. We need a kernel binary, which is the core of an operating system. We need a disk image. So what is disk image? So basically, when the computer, your computer or a computer system is turned off, most of the important data, application, operating system, kernel, bootloader, anything is actually maintained inside the disk, the storage. And it's sort of like a non-volatile memory. So that's the important thing about disk. A disk image is actually a descriptive file for this storage. It just shows what is the structure of that storage, what data is available there. And also we need the workload binaries as well. So once we have everything ready, we can launch a full system simulation using the gem5 binary and your config file, and a path to your kernel, disk image, your workload, which the last three can be embedded inside the config file. Not necessarily you need to pass it through the command line. Any questions so far? No? Okay. So let's see what is booting up a system. What steps do we need to take to boot up a system? So once you turn on your computer, the very first thing that happens is that the BIOS, basic I/O system, input-output system, is executed. So BIOS is a software which is maintained in a non-volatile ROM chip on the motherboard, and it performs some hardware initialization during the booting of the system. An important thing that it performs is that it launches bootloader. Let's see what bootloader is. So as I mentioned before, once your system is turned off, every important thing, such as operating system, is maintained inside the storage, the non-volatile memory. But once your system is turned on, your computer basically needs that operating system to be brought up into the main memory or working memory. That is the job of the bootloader. It tries to help operating system to reside inside the working memory. So immediately after your device starts up, a bootloader is launched by a bootable medium, usually the disk, the hard drive, and the information about how it should be launched, where it resides, and things like that is given to the bootable drive by the BIOS or the firmware. So as I mentioned, the important thing the bootloader does is that it launches kernel, it brings the kernel from the disk into the main memory. Let's see what kernel is. So kernel is the heart of an operating system, and it has complete control over everything inside the system, including, so it knows applications, it knows CPUs, memory, devices, everything. And the primary residence area for the kernel is the main memory. So it helps to orchestrate everything from application, CPU, hardware, software, everything together. And the most well-known one is the Linux kernel. Another important thing about how a kernel manages all of the devices together is device tree binary, which is basically a data structure, a tree data structure that describes the hardware components of your computer. And in this way, operating system kernel can manage those components: CPUs, memories, buses, interconnects, integrated peripherals, things like that. So now we have reached to a point that we know that kernel, for example, Linux, has been booted. Not booted completely, I mean, has been brought to the main memory. So the next things that I'm going to discuss are specific to the Linux kernel, might not be applicable to other types of kernel. But the next step for Linux that we can take is that systemd is executed. Systemd is a system and service manager. It's a program, and it acts as like a glue between the user space and the kernel space. So it helps us, the user, to basically log in as a root through another program, which is called Serial Getty Service, or GETTY service. And after the root has been logged in, another program is executed, which is bashrc executable. And this is, again, another script file that is executed automatically when a user has logged in. And it contains a bunch of configuration for some terminal session that gives control to the user once the system is booted up. So once we reach to this step, we can say that the system is fully booted. Any questions so far? Okay. So we saw all of these steps, and we discussed what happens in each stage. But let's see what happens for gem5 booting steps. So what I want to emphasize here is that the first two steps does not happen in gem5. Gem5 cannot simulate BIOS or bootloader. It just assumes that kernel is in the disk image, and it brings it to the main memory, and that's where booting chart or booting flow starts for gem5. Another important thing is that things like systemd is optional. One may choose to use other types of user-defined initialization app or services if they have anything else. Questions? Okay. Let's see why this image matters. Why did we decide to go through all of these steps? So the important thing that I want everybody to understand here is that there are a lot of programs, data that are executed here, and most of them are actually accessed through disk. So like the primary maintenance area or storage for those important things such as bootloader, kernel, all of the other programs such as systemd and other things, bashrc, they all reside in the disk. So it's important, once we are creating our disk image, we provide proper files and programs into it. We load all of them into the disk image. So once we start the simulation, we enable this chart of booting to happen. So we can successfully boot an operating system like Ubuntu or something like that on gem5. Questions? Okay. Let's see how we can make a disk image by Packer and QEMU. First, let's define the disk image once more. Disk image is actually a file that contains the content and the structure of a data storage device, such as hard disk, SSD, whatever that you have. A disk image is usually made by creating a sector-by-sector copy of your source medium. For example, and it can replicate the structure and the content of your storage device independent from the file system. So it just has the content, nothing related specific to a device. And the file format can be any of the open standards. For example, for optical disk image, it can be ISO. And the size of it is expected to be pretty large because this usually hard drives are large. If you want to have a sector-by-sector copy of that, your descriptive file is going to be large. So that's one of the reasons that full system simulation is usually very, very slow compared to like launching a full system simulation. Preparing a software that is usually much longer than SE mode. There are many ways that you can create your own disk image. You can use gem5 utils, you can use QEMU, and you can use Packer. So gem5 util and QEMU, they can be independently used, but Packer is actually used to make the second one. The QEMU happen some of the steps of it automatically. So you can use it for x86, but if you want to make a disk image for ARM or RISC-V, you probably have to use QEMU. So just a heads up there. So in the next slides, we're going to see what happens when we use Packer to create a disk image. So we use Packer and QEMU together to automate the process of creating the disk image. QEMU is actually responsible for setting up a virtual machine, and it controls the interactions with the disk image during the building process. For example, it installs Ubuntu to the disk image. Packer does not handle that. It copies the files, for example, your benchmarks, your bashrc, systemd, or any other shell script that you need to be run on your disk image into it. And again, it can run scripts on the disk image after you install Ubuntu on it. So we won't use in the example that we're going to see, we're not going to use QEMU directly, but we use Packer, which provides a simpler interface to interact with QEMU using a .json script. So using this .json script, we make a lot of steps that you need to do manually with QEMU to happen through that one script running. So for this purpose, I'm going to use an example from the gem5 resources, the NAS parallel benchmark, NPB. So we're going to see what happens in the files that they have provided for that benchmark resource for creating a disk image functional for that specifically. NAS parallel benchmark is basically a set of HPC workloads. It's highly used, so I thought that it's a good example to start from. So if you, I'm not going to switch to code space, but if you want to see the exact and complete content of each file, you can start from gem5 resources, source NAS parallel benchmark disk image folder. Everything that I'm going to discuss is inside the disk image folder for NAS parallel benchmark. So this is what they have in the build.sh, which is a shell script that we use to launch the process of creating the disk image using Packer. The first thing that it does is that it gets a kernel, downloads it, and it unzips it, and then it validates the npb.json file, which is the main script that is going to be launched. And after that, it checks that it's validated, it builds that JSON file. Very simple. So this is the content of the NAS parallel benchmark.json file for creating a disk image. It's a very large file relatively, so I have divided that into 3 sections. The first section is builders, the next one is provisioners, and the last one is the variables. The builder is actually a setup like configuration for the virtual machine that's going to be run by the QEMU, and a setup like password users, so it can actually log in once the Ubuntu is installed on it. So it's more like a configuration file. The provisioners are actually the files that you need to load into your disk image. This is probably the part that if you want to modify a disk image that you need to change. For example, if you add some M5 ops or things like that to NAS parallel benchmark and you create your own version of it, you need to probably change some of the files that are here. The first one is basically M5 ops built already, and they just copy it into a destination inside the disk image. The next one is serial gateway service that we discussed and explained that this is used to allow the root to log in once the kernel is booted. The next one is a run script that we're going to see the details of it, that is going to be used to actually run the benchmarks during runtime when gem5 full system simulation is happening. The next one is actually a file that is specific for this benchmark, which is creating some information about the workloads of this benchmark. The last section is two executable files. One of them is post-installation that takes care of a couple of steps after the Ubuntu is installed on the disk image. And the last one is npm install.sh is a shell script file to basically compile the workloads into the disk image. We're going to see the details of these two files later. And the last section, variables, is basically, again, some information to be set for the configuration in the first section. You can assume that the first and third sections are usually generic. You probably don't need to change those. The most important ones, once you want to modify or change a gem5 resource, is the middle section. Questions? Okay. So we saw in the previous slides that we have two important files. One of them is post-installation. The other one is npm install. Let's see what's inside each of those files, because they're going to be executed serially into the disk image. So post-installation.sh has a content like this, which basically is going to be executed right after the Ubuntu is installed on the disk image. So it first moves the serial getty service file into another directory, which is for systemd. So it allows systemd to, once it's executed, to execute serial getty, allowing the root to logged in. And then it moves M5 to sbin directory. This is for convenience. The next line also is for the convenience. Basically, they want to put like M5 and gem5 into the path, so they don't have to provide the full path of these two when they want to run something on the disk image. They just say F5 or gem5, and they can run it. The last line is the important one, which actually puts the run script, the main run script that allows us to run our workload during the simulation into the, basically copies the entire thing that we put into the run script at the end of the bashrc. And we saw that at the end of the boot chart, bashrc is executed. So it means that automatically our program is going to be executed as a part of bashrc. Questions? The next one is npm install.sh. This is specific for NAS parallel benchmark, which basically tries to install some like dependencies that is required for NAS parallel benchmark, such as a G4tran compiler. And once all of those stuff are available, it goes to that directory and it tries to compile using main and a bunch of dependencies again and flags. So after this step is done, it means that we have the compiled code of NAS parallel benchmark into our disk image. We talked about run script, and we saw that it's going to be like being added to the end of bashrc. So it's an important step that, again, probably if you change your, if you want to have your own version of NAS parallel benchmark, this is again one of the files that is probably needed to be maybe changed. For example, if you want to add more M5 options and things like that. So what happens is that at first it calls M5 read file, and it puts that into another shell script, which is called a script.sh. So if you remember, once you are making your configuration file for your full system, in some sections, you make a command here, and then you put this command into read file content. I think you saw this yesterday for some of the examples of Gem5 standard library and resources. So once you have taken care of these two steps on the right in your config file, and you're creating your disk image, once it reaches to this line on the left, M5 read file, it puts this command into your shell script, and we know that, into a script.sh, and we know that this script.sh is going to be added at the end of the bashrc. This is how we enforce sort of execution of our programs to be a part of, to be an ending part of the booting flowchart. So, and once we have those things available in the script.sh, it checks whether actually we have put something, that there is a bug or something like that, that read file is empty. If there is a content into it, it makes it a script.sh to be an executable file, and then it runs it. After it finishes the run, it calls M5 exit, and that's the end of the simulation. So this is like a combination of most of the things that we have seen together in the past couple of days, having M5, M5 ops, read file, and now we can see how they are actually used all together during the full system simulation. Any questions?
It's a good time for questions.
Yeah.
This is a little weird in that, we're using this special M5 operation to communicate from inside the guest running on the simulator to the simulator. Or I guess in this case, the command over on the right-hand side is something that the simulator has. That's in your Python run script that's executing the simulator. And then we're communicating that information into the guest. So then the guest can actually execute that string. Does that make sense? It's something that's just like, and all y'all are way smarter than me, because it blew my mind for a long time. Okay. Either they all get it or they don't understand it at all. I can't tell them.
Okay, at least we can say that. Oh.
So the command home, is that a command that's running?
That command, after Ubuntu boots up, the guest boots. The guest will execute that command inside the guest running on top of the simulator.
So is that on the disk image?
Yeah, so we copied all the NASCAR benchmarks and on it.
Run script command actually executing those commands.
Yes. So the command there actually executes those commands inside the guest running on gem5. Oh good, I'm now seeing confused faces. I like this.
I wonder what script, like that script.sh that was like added. If you now, the simulation ends and you opened up the disk image, will that script.sh be populated or not? Is it permanent?
That's a great question. Do you want to answer that?
You can go ahead.
Okay. When you set up your systems, one of the things you add to your system is an IDE controller. That IDE controller has a disk image as part of it. So when you issue a DMA read to the IDE device, it reads it off that disk image. When you create that disk image, you have the option of making it copy on write or not copy on write. Almost always you want copy on write, in which case any modifications to the disk image will not persist between multiple times. You don't have to do that. You can make you can do it so that changes to the disk persist. But then it becomes really hard to experience.
Yeah, it's also you look out at the benchmarks.
Yeah. Also with copy on write, you can have a bunch of simulations running in parallel using the same disk. Whereas if they weren't doing copy on write, they would be mucking all over the same disk.
Oh yeah, so then if you couldn't have two scripts running the same, right? Because then they both collide on that script.sh.
So every execution of gem5 will be using a in-memory copy of the disk. It's the same. It'll be the same image file on the hard drive on your host, but a different in-memory copy for every process of gem5. Great question. Other questions? This is when it starts getting really mind-blowing. Yeah.
Instead of having a predefined script, can we like interactively interact with the?
Absolutely. Maryam's going to give you an example of that in a few minutes.
Okay.
don't you have to keep putting the firmware into the computer?
So in this
Like,
example, you have to boot the kernel every time. Which, with these scripts, the NPV, it uses KVM to boot, so it boots like that. Like literally less than 10 seconds to boot that.
how is that?
But yeah, you could boot taking check one, which is often what you do.
So basically, another example which is we're running from another operating system.
Hi. Yeah, you can think of that.
Just follow up. You're setting that copy of right variable. Is this the JSON you're creating it? It's like, is this when you're creating it, or is this where do you set that?
Set what?
Where do you set copy of right? I think that's primary you're talking about. How do you, where do you
Sorry, say that one more. This AC is really loud.
where do you decide to set like that primary copy of right or not?
Oh, that's in your Python run script.
Oh, every so like that config script.
Yep, exactly.
Oh wow.
So it's buried somewhere in the standard library, since you almost never want to change it, but you could.
Very perfect.
Cool. Any other questions? Awesome. Why don't we take 5
Sure.
and get some coffee
Yeah.
and donuts, and then come back
Continue.
and continue on. I think it's a good place. Right? You're about to move on to.
To kernel, and then this is the end of this section. Goes.
So let's go ahead and take that. All right, take 5. Let me say real fast, I know it's getting hot in here again. So, reminder, there's bottles of water in the fridge. There are plenty of cups here. And you can steal cups for tea as well to get ice and water, either bottled water or from the tap or from the water machine in there. So, stay cool. We'll run the fans. Let us know if there's anything else we can do.
Okay, so we saw how we can make our own disk image based on the programs or whatever else that we need. Here I have another example for how we can make our own kernel binary instead of using whatever that is provided as pre-compiled kernels. So again, I am borrowing this from gem5 resources, where we have a specific resource explaining how we can compile a Linux kernel. So it's pretty straightforward. You just have to download the kernel, the Linux. Here the example is about Linux. Getting it from the Git repository, and then you check out the specific version that you want, and then you copy a file, which is config.whatever version that you have, into a specific file which is going to be used during compilation. So by hitting make -j number of threads that you want to allocate, it's going to start compiling, and at the end, a compiled kernel binary, which is VM Linux, is going to be put in a directory called /Linux. If you want to use like your x86 machine to compile a kernel binary for, like, let's say ARM, again, a reminder that you need to use cross compilers. Okay, so we're not going to do any example here. This is just for your information to know that if you wanted in the future to do compilation for your kernel, this is how you should do it, and it's available in gem5 resources. So the next thing that I want to explain is how we can modify or extend gem5 resources. The thing that Bobby discussed yesterday about the standard libraries or gem5 resources with your own kernel, for example, or the disk image that you have created. I think you have seen a couple of examples probably, But here is another time to repeat those things that, just as a reminder that this is how it should be handled. So, for example, if you want to use x86 NASParallel benchmark.py, this configuration, and you want to, instead of using whatever already available on the website for NASParallel benchmark, instead of that, you want to use the disk that you have created or the kernel that you have compiled, you need to use custom resource. You just import it as custom resource. For disk image, we have another custom resource which is called custom disk image resource. Gives you a little bit of more features to interact with the disk image, like accessing the partitions and things like that. But custom resource works for both kernel as well as disk image. And then once you imported these two, or one of them, the first one, inside this section, set kernel disk workload, you need to use kernel equal custom resource, and then you specify the path to the kernel that you have generated. The same thing for disk image as well. You specify it using it. And then a path to the disk image that you have created. In this way, everything else should remain the same and just should be fully functional. Don't need to change anything else. Questions? Okay. Just again as a reminder, so gem5 resources have a lot of pre-built resources, many like disk images for different ISAs, as well as kernels. Definitely for RISC-V and x86. We have some for ARM as well. If you wanted to get them directly and just use them in your simulations for different purposes, you can consult the file, which is resources.json in gem5 resources. We have all of the resources registered there with all of the information for them. If you want to directly download them, you just have to take the URL base, add that with the specific URL for that resource, and then you have the full path, and then you can use, for example, wget or something like that to download them for yourself. And if you want to create a new gem5 resource, you need to register that inside the resource section of this JSON file. It has many, many examples. You just need to create a new entry for your resources. It's probably good for your usage, but it's not going to be available in the gem5 resources main line. If you want to do that, then you need to take another steps, which I think is going to be discussed on Friday.
This is a great way to contribute. We would love to have more resources.
Okay.
Probably will figure out how to make it easier to contribute. More work for me. But we make lots of work for them and then automate. Let's force them to automate.
Okay, this is the end of this section, and then we're going to see a very useful tool which is called M5 term and how we can use it. So M5 term tool, or M5 term, is actually an API that gives you access or to the simulated console interface that the full system gem5 provides. So it means that, for example, you have launched a full system simulation. You're seeing a lot of things are going on inside your terminal, but that's the host terminal. If you want to see what's going on in the guest terminal, you need to use M5 term. It's a good way to see, what's going on there. If you want to do debugging or just control what happens there, it's a very useful tool. So just like M5 ops, you need to make it, build it, and you just need to simply go to the gem5 util term and hit make. It should build it for you. So I'm going to ask you all to do these two commands so we can continue our example. Just simply go to the gem and make it. Everybody built the M5 term. Oops. Okay. So the format is like this command. So you can say /m5 term if you are within the directory or giving a full path to the M5 term that you have built. Then you have to, for example, localhost if you are trying to connect through the host to the guest, and then the port. You have to specify a number for that port. So the question is, what port number you should use. Launch your full system simulation, keep an eye on the terminal, and try to find like system.platform. Pull that number and add it to this command, hit it, and then it's going to be connected to the host console. No, sorry, guest console. And by default, gem5 is going to use the port 3456. Like run up until it finds something available. And there are like special characters to escape or to end, to exit, like dot. And if you're interested, you can see the documentation for this purpose. Okay, now let's do a very, very simple example, which is available on the materials using gem5 full system, and it's called risk5 full system.py. So this this example tries to quickly launch a kernel on risk5, and we can use this small example to use M5 term to connect to the guest terminal. So hopefully you all have the risk5 gem5 binary that we tried to build in the beginning of this session. So you just need to have a path to your gem5 binary and a path to this configure script for risk5 this.py. Just hit it. It has to the full system simulation, and then you can find the port number. Once you have the port number, try to launch a separate terminal, and then use this gem5 util term and 5 term localhost and the port number. You should be able to connect to the guest terminal console. I'm going to ask you to have the slides open if you want to have access to these commands, because I'm going to move to code space to what's happening. Okay. These examples, so this example is, the way that it works is like this. So it launches the full system. It tries to boot up. During the boot up, it's going to ask the user, the one that is simulated, it's going to ask the user to provide a username and a password. So you have not provided that, the booting session is not going to complete. So you have to use M5 term to access the guest terminal to use the user pass, so you actually can help that simulation to finish booting. The user and pass is both are root, if I remember correctly. ROOT. It's also has been written in the config file. Material. So again, in my system, the default port was available, so I'm going to use the same number. It's going to take a while because it's working in the background. And maybe after, I don't know, hopefully a couple of minutes, it's going to ask you for their password to log in. You can use root for both, and then you're done. You can actually play within that terminal, which is actually the guest terminal, like using commands like ls or cd to different directories, which is for the file system of the system that you have simulated. But it's going to take a while. What do you mean? Yes. If it finishes the simulation, you can see the stats. Yeah. It's keeping all of these stats updated. If you want to read the stats, you have to wait until the simulation finishes. So it actually generates this stat.txt, but it's recording and logging all of these stats as you are working.
Is there, you use the util for command line, right? So let's say you're LSing around, can you use M5 or something to reset stats? You may or may not.
Yes, I don't know any reason why not, so the answer should be yes, yeah. That's a good question. Maybe it's timing. No, it's actually. Can do that, but it's very difficult. Like this terminal one. You don't have any way to install it. You know, it's difficult. You can do this. A very inefficient way of doing things. But I think it's completely possible, but completely inefficient. Yeah, if you copying from host to guest, I don't think the M5 term would allow you to do that. What it was file from scratch. It's difficult, but I think it's possible. written in the config file. Sorry, let me double check the config file. Materials. Yeah, it's root. Yeah. After a while, those who were able to access the terminal, they can play with it, like running some commands, ls seeding to different directories, see what happens. Yeah, I started late. I'm almost finished. This is the end of my presentation. Okay, then M5 exit directly. Try that. Okay. So everybody was able to access the terminal, fully booted, right?
So just to be clear, this is running a full system under gem5. So everything that's going on, we're collecting, gem5 is collecting traces, as we're using the atomic CPU so it's fast, the atomic CPU is executing everything one instruction per cycle, etc. So this is, you're simulating a full system.
What is that?
Oh, it's M5 not on this?
It's not on the path.
Okay. Well, never mind. So M5 is
Okay.
so on the okay, so we can stop the simulation. Look at the stats. 0.8 seconds. And so we did the boot line, jump 5 seconds boot line.
Okay. Yep. That's the end of my presentation.
Any other questions? About using full system simulation?
Do you have a question?
Okay, great. Let's do another fiver and be back at 10 after.